Hello friends, so today we are going to learn engineering mechanics, and in engineering mechanics we are going to learn a topic known as kinematics of rigid bodies. So kinematics of rigid bodies, in this topic we are going to learn about the motion analysis of rigid bodies. As we know that kinematics is that part of engineering mechanics where we don't deal with the forces. So here we are going to deal only with the motion analysis of rigid bodies, and in this topic we are going to specially learn a method known as instantaneous center of rotation method. So first we are going to learn what are the types of motion. So basically three types of motion will be discussed over here. The first one will be translation motion, next will be rotation motion, and third one is the most important method for which we are going to learn ICR method. And this motion is known as general motion. What is general motion? General motion is the combination of both translation motion and rotation motion. So my dear friend, let's see the first example of translation motion. So here we have seen a rectangular object is sliding in the rightward direction. So this motion is known as translation motion, and I have named the mechanism as slider mechanism. Next, let's consider rotating mechanism. Here the black body will be rotating about the blue body, so this body is rotating about a fixed center, and such a mechanism will be called as rotating mechanism. Here I have taken example of slider crank mechanism, where we can see that this green body is continuously rotating, and because of the rotation of this green body, this blue body is translating or oscillating in the red slot, and there is a body in yellow color which is connecting both blue body and green body together, and this yellow body is known as connecting rod. So here we can see that the body which is in pure rotation is green in color, the body which is in pure translation is blue in color. So this can be called as rotation or crank mechanism, whereas this will be called as slider mechanism, and both slider and crank is connected with the help of a connecting rod. This connecting rod is a combination of both rotation and translation. You can see that this end is continuously translating and this end is continuously rotating. That means this body is in continuously both in translation and rotation motion. So this body can be called as a body in general motion. So what is general motion? As we have already discussed, a body which is in both translation and rotation motion together. What are the examples? The tire of a vehicle, the wheel of a vehicle. The vehicle moves forward direction because of the rotation of the wheel. So we can say that the wheel is both translating and rotating together. So the wheel is the best example of general motion. The connecting rod of slider crank mechanism as discussed in the previous slide. Also, if a ladder is falling both with the help of wall and the ground, let us say that this ladder is going to fall from this position to this position. So we see that there is both angular displacement as well as linear displacement. So angular displacement and linear displacement together is nothing but sliding and rotating. So this is an example of general motion. So this is an example of general motion where body is having both sliding and rotation, both having angular and linear displacement. So we can also assume general motion in our body. Our body moves forward because of the angular displacement of our legs. So the extremities of our body causes the running and walking exercises. Also the riding of the bicycle with our legs is an example of general motion. So we are going to learn instantaneous center of rotation, as we are studying this topic only to learn what is instantaneous center of rotation. So we focused all our discussion about the general motion, which is combination of translation and rotation motion. So a body in general motion is nothing but a body which is both rotating as well as translating. So we'll assume that a body which is in general motion, a body which is in general motion is assumed to be in pure rotation. A body which is in general motion is assumed to be in pure rotation about some point, and that point changes at every instant. Since the point about which the body is in pure rotation changes at every instant, that is why we say that this center of rotation is known as instantaneous center of rotation. So we are going to learn instantaneous center of rotation method. Now the very first example which we are going to discuss is about this crank. Here there is a crank which is rotating. The crank is not visible, but rotation is clearly visible. So the crank is rotating continuously, and that it is connected to the connecting rod, and that connecting rod is further connected to the slider. So slider is continuously oscillating and the crank is continuously rotating. So the crank is rotating about its center always, and its center itself is its instantaneous center rotation. So my dear friend, do remember that The instantaneous center of rotation of a pure rotating body is nothing but its center of rotation. Next, we are going to discuss the slider. This slider is continuously oscillating about the sliding surface, and its ICR will be perpendicular to it, lying at the infinity. We are going to repeat these things again and again. Okay? Since this body is in pure translation, this body is in pure rotation. Since this body is in pure translation and this body is in pure rotation, we know that the body in pure rotation, its ICR is nothing but its center of rotation. The body in pure translation, as we have just discussed, that its instantaneous center of rotation lies perpendicular to it at the infinity. The same way the surface on which we walk, it is a surface of the earth, which planet is circular, it's spherical. So we are walking on a spherical surface, but we never feel that spherical surface because of very long distance of the earth's radius. So that is we can correlate the things, and we can assume that the body which is in pure translation is nothing but a body which is rotating about an infinite radius. Is that okay? So the third body, which is the connecting rod, is body in general motion. The third body, which is the connecting rod, is the body in general motion, and its instantaneous center of rotation will be located with the help of Kennedy's theorem. So let's see the example. I have drawn the schematic of the previous question, and here the red one is our crank, which is in pure rotation. Its rotating path is clearly shown. The blue one is our slider. So slider is continuously oscillating, and its ICR lies at infinity, and we have discussed that its ICR will be perpendicular to the surface about which it's sliding. The crank is rotating about its center, so its instantaneous center of rotation is its center itself. Am I correct? Now we are here going to discuss the ICR of the connecting rod. The connecting rod's ICR will be located with the help of a theorem known as Kennedy's theorem. What does the Kennedy's theorem says? If three bodies are in relative motion to each other, their three instantaneous center of rotation will lie in a straight line. Let's see how we have located the ICR. So what we have done, we have extended the rod. Okay? We know that this is one ICR, this is the second ICR, and the third will be on the straight line. Similarly, there is one instantaneous center of rotation at the contact surface of the sliding surface, one at the infinity. So the third one is over here. So this is how we are going to learn how to intersect two lines and get the ICR of a body in general motion. So this connecting rod is in general motion, which is rotating about this instantaneous center of rotation. This yellow connecting rod is in general motion, and this is rotating about this instantaneous center of rotation. Now location of ICR of a body which is in rolling. So we have discussed that a wheel rolls and the vehicle moves forward. So if a body is in pure rolling, that means there is no slipping. Its instantaneous of center of rotation will be the point of contact between the wheel and the road surface. Do remember this. The instantaneous center of a wheel which is in pure rolling, there is no slipping. The instantaneous center of rotation is nothing but the point of contact between the wheel and the rolling surface. We have discussed where does the sliding object's ICR is. So the sliding object ka ICR is at infinity and perpendicular to the sliding surface. So we have drawn a perpendicular to the sliding surface, and I have shown that it lies at the infinity. So third one, how to locate the ICR of a connecting rod? Just extend the crank, just draw perpendicular to the sliding surface, and you are going to get the ICR of the connecting rod which is in general motion. Is that okay, my dear friend? What are the formulas involved in this chapter? The formulas involved in this chapter is V equals to R omega, or omega is equals to V by R. We have studied this formula in circular motion in 11th standard. So this formula is going to help us to find out the motion analysis of rigid bodies. So how to solve the numerical? How to solve the problems? So very first step is extend the line from the crank. What is the crank? Crank is a body which is in pure rotation. And what is the next step? Draw perpendicular to the sliding surface, and you are going to intersect both the extension as well as the perpendicular, and that intersection is going to give us the instantaneous center of rotation. So here we have a first example. Here we can see that this body AB is a crank which is rotating about this center. This C is the slider. So what are we supposed to? We are supposed to extend the line AB and we are supposed to draw perpendicular from the slider, and we are going to get the instantaneous center of rotation. So I have extended the line from the crank, I have drawn a perpendicular with respect to slider, and we have got the ICR. Suppose they ask me what is the velocity of point D, we are supposed to draw a line from D to I. So this is the radius of rotation, and with this radius of rotation multiplied by omega of body CD is going to give us the velocity at point D. Is that okay, my dear friend? Let's see the next example. Next example is again a slider crank mechanism. Though the slider is not visible over here, we are going to draw the perpendicular to the sliding surface as discussed. So let's draw extension from the crank. The crank is rotating, it is in pure rotation, so we are going to draw extension from the crank. We are going to draw perpendicular to the sliding surface, and that intersection is going to give us the ICR of this mechanism. Let's see the example 3. Again we have an example of slider crank mechanism. Draw extension from the crank AB, draw perpendicular to the slider C. The intersection is going to give us the ICR of this mechanism of connecting rod BC. Is that okay? Let's take the next example. So this example shows an example of slider mechanism. You all can see that when this collar at point B slides up and down, because of that this end at A is going to slide. Is that okay? So this such type of example is known as slider mechanism, and the body AB have both angular as well as linear displacement. So this body is in both translation and rotation motion, and this body is in general motion. So we are supposed to find out the ICR of this body AB. How to find the ICR of this body AB? As this is also a slider and this is also a slider, draw perpendicular to both the sliding surfaces and you are going to get the ICR of this mechanism. Is that okay, my dear friend? Do remember that. Let's take the next example 5. In this example 5, you all can see that crank AB is connected to connecting rod BC, and connecting rod BC is further connected to crank CD, which is hinged at point D. So crank AB is hinged at point A, crank CD is hinged at point D. So this is an example of crank mechanism. Here rotation is getting converted to the rotation. Here rotation is getting converted to the rotation with the help of a connecting rod. So whenever there is a rotating mechanism, that is crank mechanism, we are just supposed to extend the lines from both the crank, and that extension is going to intersect, and that intersection is going to give us the ICR of this mechanism. So the connecting rod BC ka ICR lies over here. Is that okay? Let's see the next example, 6th example. Let's read the example and then we will decide where does the ICR lie. So it is said that a wheel of 2 meter diameter rolls without slipping on a flat surface. The center of the wheel is moving with a velocity 4 meter per second towards the right. Determine the angular velocity of the wheel and find the velocity at point P, Q and R of the wheel. So what we are supposed to understand is what is happening over here. So it is clearly mentioned that this wheel is rolling without slipping. So we have already discussed, whenever there is rolling without slipping, whenever there is pure rolling, the ICR lies at the point of contact of the wheel and the road or the rolling surface. So here our ICR lies. Is that okay, my dear friend? Let's see the last and the next example. So here it is said that a wheel is rolling on a surface, but there is slipping. Due to slipping, points A and B has this velocity 3 meters per second and 1.5 meter per second. Velocity at point B is 3 meter per second. Velocity at A is 1.5 meter per second. Remember that there is a slipping. When there is slipping, the instantaneous center of rotation will not lie at the point of contact. It will lie somewhere on this line. How do we come to know that on line AB we are going to have our ICR? Because they have given a velocity at point B, which is the topmost point. They have given the velocity at point A, which is the bottommost point, and we know that they are perpendicular to the vertical diameter. So on this vertical line our ICR will lie. We know that velocity is always tangential and it is perpendicular to the radius. So the ICR will be somewhere on this line AB, and the radius will be perpendicular to the velocity. So this line is perpendicular to VB as well as VA. So my dear friend, let's see how to locate the ICR. So it is said that bottommost point has 1.5 meter per second, topmost point has velocity 3 meter per second. What is the ratio of VA to VB? They have ratio 2 is to 1. Am I correct? VB is 2 times VA. That means this total diameter needs to be divided into 3 parts. 2 plus 1 is 3. Now we are going to see how much distance from point A the ICR will be there. So from the top the velocity is 3, from the bottom the velocity is 1.5. So it will be over here. So this is 1/3 of the radius, this is the 2/3 of the radius, and that is going to locate the ICR. So let's see where the ICR lies. So the ICR lies at point, this green point. So the diameter AB is divided in the ratio of 2 is to 1 from the top. So 2/3 of the diameter is the radius of topmost point, 1/3 of the diameter is the radius of bottommost point. So this is how we are going to locate the ICR for different types of numericals. So we have studied in this lecture what is ICR, what is body in general motion, what are the formulas involved in finding the motion analysis of the bodies in general motion, and also we have seen the various probability of questions how to locate the ICRs. So I hope you all have understand. Do remember that we are supposed to draw a perpendicular to the sliding surface, and we are supposed to draw a extension from the rotating object, that is the crank. So do remember this slide, my dear friend. Thank you.